Good afternoon, everyone, and welcome to my talk. First of all, I would like to thank the organizers for giving me a chance to present in this OpenACC workshop. I'm Seungwu Han from Seoul National University, and today I would like to briefly introduce the machine learning potential that are attracting recent attentions in the field of materials modeling. Okay, these days, nanotechnology is driving rapid advances in IT and energy industries, such as highly scaled semiconducting devices, high-resolution displays that are used in the AR or VR glass, and next-generation hydrogen vehicles. In order to improve the performance and the durability of these devices, it is important to understand and control what happens at an atomic scale. Since the experimental analysis is limited at such a small scale, the computational simulation is very useful. There are two types of atomistic simulation: the classical potential, in which you parameterize the interactions among the atoms. The classical potential is very fast and so can deal with a large number of atoms in your simulation box. However, the potentials are developed only for a few materials, and it takes a long time and expertise in developing new potentials. Alternatively, you can simulate the materials by directly applying the quantum mechanics on electrons, which are called ab initio or DFT method. The ab initio simulation is widely used owing to the accuracy and the high predictive powers. However, because of the huge computational cost on solving differential equations, you can simulate only a few nanometers in the length scale and also a few less than nanosecond in the time scale. And in order to simulate real materials, you need at least tens of nanometers, but that is not feasible with the DFT method. Recently, the situation is changing and it is overcome by the machine learning method. In this pioneering paper, the Vella and Parinello proposed a neural network method in which you train the machine learning model by providing DFT data for reference structures and predict the energy of the new systems by inference without solving differential equations. As you can see from this citation trend, the interest on this method is growing exponentially, especially after the introduction of the AlphaGo. One of the key ingredients in the neural network interatomic potential is the feature vector, or how to encode the local environment around certain atoms. The Vella and the Parinello are proposed to use symmetric functions that parameterize local radial or angular distributions. The main advantage of the symmetric function is that it secures invariance on the rotation, translation, and permutation, as well as smoothness. And these characteristics enable efficient training. Recently, the graph type descriptor is also suggested. And from our preliminary test, it is more general and accurate that the Vella-Parinello type symmetric functions. And so we are keen to this method as well. So the main advantage of the neural net potential is the computational performance. So in this example of the crystalline silicon structure, the x-axis is the number of the atoms, and the y is the time that requires to perform a certain amount of the computation, and they are in log scale. And you can see that in the case of the DFT calculation, the computational time increases with the cubic scaling with respect to the number of the atoms. So computational time increases very rapidly. On the other hand, neural net potential or the classical potential, the computational cost increases only linearly. And therefore, even for small size of the atoms, you have 1,000 times the speed up compared to the DFT. But in the case of the large number of the atoms, then this gap increases much more, bigger than like the million times or maybe the billion times. So therefore, the machine learning potentials allow for the MD simulations at the DFT accuracy up to 1,000 atoms or 10 nanometer feature scale over the time scale of a nanosecond. Therefore, the machine learning potential has expanded the scope of the DFT calculations by this amount. And I emphasize that this is we do not sacrifice any accuracy. This is at the accuracy of the DFT level. we have developed our own in-house machine learning potential package based on Bell and parameterized symmetric functions. And it is called the simple NN, which is a short name for SNU interatomic machine learning potential package, the Persian neural network. And it is open at the GitHub. And this package takes the DFT training set, such as the total energy or atomic force or stress tensors that are calculated from the popular package of the PASP or open software Quantum Espresso. And the package generates the G vectors, which is done on the CPU, and it supports the input pre-processing with the MPI parallelization. And also it trains the neural network via PyTorch, which is done on the GPU, which is many times faster than the CPU. In carrying out the MD simulations, we are using the LAMS package, and there are interfaces are developed between the simple NN and the LAMS, and they are done on the CPU. Okay, so for the last few years, we have developed this package, and also we published the papers on the fundamental understanding, and also the sampling method, training method, and uncertainty quantification. And also we apply the method to diverse applications that are important in many material science or the engineering. And all of these calculations are far beyond the scope of the DFT calculations. So in the following slide, I will demonstrate a few of these examples. The first one is the nuclear solicitation. So this process is very important in the semiconductor processing in order to reduce the contact resistance between the silicon and the metal electrode. So this is basically you are inducing the chemical reaction between the nickel and the silicon. And in the case of the DFT calculation, you can simulate only this size of the computation. So it is just only 1 nanometer and maybe yes, hundreds of the atoms. And this is one you can obtain with the DFT calculations. On the other hand, if you train your neural net potential, then you can simulate much larger the scale. You can see that. And also in terms of the time scale, you can simulate much longer simulation. This looks much more realistic. Okay, and you can see how this interaction proceeds or the reaction proceeds because of the nickel and silicon contact. Next example is a core shell quantum dot, which is important in display devices. In the case of the DFT calculations, you can simulate only small size quantum dot. This is indium phosphate, which is the core surrounded by the zinc selenide shell. And this is much smaller than what is actually used in industry. On the other hand, with the machine learning potential, you can simulate the real size quantum dot that is used in actual display. And this is the composed of the 1 nanometer and the 1.5 nanometer core shell thickness that encompasses more than 3,000 atoms. And from these simulations, we obtain the phonon spectrum or atomic vibration. And with that, we can calculate the emission spectrum. So this gives you an idea how sharp is the light that coming out of the quantum dot. And the green line is what we have obtained from the simulation of this structure, and which agrees very well with experimental measurement. Okay, so this is the possible because we have introduced or simulated on the real scale quantum dot. The next one is the crystal structure prediction. So this is like the well-known protein folding problem, in which, given the sequence of the amino acid, you predict a three-dimensional protein structure. So this is the inorganic crystal version of the structure prediction. So here, you provide only the composition, how many atoms, what kind of atoms in the crystal, and you try to predict the structure that is the equilibrium or the lowest in the free energy. So in order to find the lowest configuration, you have to navigate a huge number of the diverse configuration that are possible with the given composition. And so it is a so large astronomical number of the configurations. So one usually apply heuristic approaches such as the genetic algorithm or the permutation mutation and try to find optimal solution from the generation. Okay, so by combining with the density functional theory calculations, people have been found successfully find the structures such as the superconductor under high pressure or the energy materials. But as you can see from these examples, they are quite simple, only the binary system. So this is limited by the density functional theory calculation, which takes a very, very long time to calculate those energies. So if one can replace energy, computation, the DFT energy with the machine learned potential, then we can accelerate or we can attempt to find more complicated structures. That's what we have done in this paper here. We developed a package spinner, which combines with heuristic approach with machine learned potential and with the help of the high speed of the neural net potential. We were able to compute on very complicated tunnel structures. And this is a blind test. So the experimental structure or the ground truths are known for these compositions. And we try to find those structures as if we do not know the structure. Okay. And for the test materials, we have achieved about 80% success rate. That is to say, for most of the materials, we have found structures that are exactly the ground truths. Okay, so this is the very useful technique, and so this will be used in finding the new materials. For example, a new kind of the solid electrolyte materials that is very popular these days. However, I would like to emphasize that machine learning potential is a data-driven DFT calculation. Therefore, this is the data is everything, and the success rate, success of the potential depends on whether we can find or provide a proper training set. So there are the local environment space around a certain atom, they are huge. And so given a target simulation, it is important to take or to choose the training set that widely wrap around those target simulation. So for example, in this case of the large size nanoparticle, in order to sample the core region, we provide structures in the bulk structure, and also the phase, the area is represented by the surface structure, and those corners, we provide the reference structures are the small size nanoparticle. And so examples like these are quite straightforward to find the training set, but in many examples, the find the right training set is quite tricky, and it takes many iterative procedure to have the accurate and the versatile machine learned potential. As I mentioned, the machine learned potential has expanded the scope of the ab initio calculations, in the length scale, also the time scale. So the length-wise, maybe this machine learning potential is enough to simulate various semiconductor process or many material processing that is used in the industry. However, still we have a huge gap in the time scale. So even with the machine learned potential, we can simulate only tens of the nanosecond, which is far shorter than, maybe billion times shorter than the actual processing time that occurs in the industry. So in order to overcome that time gap, we have to introduce so-called kinetic Monte Carlo simulation. So here in this simulation, rather than focusing on the atomic trajectory, we focus on the event or the state-to-state jump in this Markov chain process. And so if we can identify those states, then one can simulate the long-time simulation, long-time calculations using the kinetic Monte Carlo method. So however, the problem here is that the reaction or the events are not obvious from what we see on the simulation. For instance, this is the one instance of the oxidation, platinum oxidation process. And from this picture, it is not obvious how the atoms will move in the next stage. But there is a method that can identify the saddle point or the reaction path using the diamond method. And in this method, given the initial condition using the two images, the method can identify the saddle point. But however, the computation of this trajectory or the saddle point identification, it takes a large number of the computations. So with the DFT, it is highly limited. Again, by introducing the machine learned potential, we can use such a brute force search method with machine learned potential. Okay, so this is what we have done in this calculation. So at this oxidation snapshot, by applying the diamond method repeatedly, we have identified the relevant chemical processes such as oxygen penetration or the oxygen diffusion or the platinum protrusion. Okay, so the chemical reactions can be automatically identified by combining such a zero-point search method and high-speed machine learning potential. In conclusion, machine learning potentials enable atomistic simulation to level beyond DFT limitations, and many industrial issues could be addressed by introducing machine learning potential, but the challenges remain for constructing the training set efficiently, and difficulty varies depending on applications. The more general and systematic approaches are in need. And the new venue of the materials modeling, like kinetic Monte Carlo simulation, now opens up by taking advantage of the speed of the locality of the machine learning potential. Okay, thank you for your attention.